Let's look at RC circuits. So RC circuits are made up of resistors and capacitors and sometimes power supplies. So let's review the components a little bit. So the resistors have symbol R, and the unit is ohm, and the symbol for the unit is the capital letter omega. And we know that resistors resist the current flow. Then we have capacitors, and the symbol is capital C, the unit is farad, and the symbol for that unit is capital F. And we know that capacitors in a circuit can accumulate charge on their plates, so they can charge up or they can discharge. Now, RC circuits are built with both of these components, and here would be an example of an RC circuit. So I have a resistor, I have a capacitor, and I have a power supply, and there's a switch here. So if I close the switch down here, what happens is I include the power supply, the battery, in the circuit, and there will be a current flowing in this direction. So the purple line over here shows what happens when the switch is closed in this direction. Now, if the switch is closed that way, then the battery is no longer in the circuit because there is a broken wire over here, so it's closed this way, and the capacitor can discharge, and this orange line shows the discharging direction of the capacitor. So let's start with the first one. We're charging the capacitor by closing the switch. In this case, the battery becomes part of the circuit, and we know that charges flow from the positive, from the higher potential to the negative potential in the circuit. So it goes in this direction counterclockwise, and the current will pass through the resistor and deposit charges on the capacitor. So the capacitor plate here will become positive, same as the charges on this plate of the battery, meaning that this side of the capacitor will be negative charges. The current will keep on going through this circuit until the capacitor becomes fully charged. Now, it gets harder and harder to deposit charges on the capacitor because of electrostatic forces between these two charges. So the very first charge that came onto the empty capacitor had no problems depositing itself on the capacitor, but when the second charge came along, the first charge had to move far away, so it was at the very ends of the capacitors, say, so that the electrostatic force between these charges would be as small as possible. Then a third charge came along, and they had to distribute themselves in such a way so that, again, to minimize the electrostatic force on them, but that force becomes stronger and stronger, and the more charges there are here, the more electrostatic forces between them, and the harder it is for the charges to deposit themselves on the capacitor. So that's why we have this behavior for the charging of the capacitor. At time equals 0, when we first close this switch over here, there is no voltage across the capacitor. All of it is across the resistor because the current is free to flow through the resistor. But then the more charges that accumulate on the capacitor, the higher the voltage on the capacitor and the lower the current that's passing through the resistor. So then the voltage across the resistor decreases until the capacitor charges fully and it lets no current go through anymore. So at that point, the capacitor has all of the voltage that was provided, the resistor has no voltage on it, and the circuit is broken, meaning that there is no more current flowing through the circuit. At that point, we can close the switch in this position so that now that the initially charged capacitor will produce a current in this direction. All of these positive charges will want to run away from all of those electrostatic forces that act on them, and this would be an escape route. So the current will flow in this direction and discharge, the capacitor will discharge through the resistor. We would have a diagram looking like this, a graph looking like this. Initially, the capacitor was fully charged, it had the voltage across here, and then the more charges that went through and balanced basically the positive charges that had been here with the negative charges, the less voltage there would be on the capacitor, and the capacitor will discharge to 0. Now the behavior of the resistor looks different. We start out with a negative voltage because the current flows in the opposite direction. When we were charging the capacitor, the current was going counterclockwise with the resistor. Now that the capacitor is discharging, the current is going clockwise, so we have a negative voltage. So if we were to draw a vertical line anywhere along here, when we add the voltage across the capacitor to the voltage across the resistor, we should get 0 because there is no battery in this circuit providing any voltage. But if we were to draw a vertical line here, the voltage across the resistor plus the voltage of the capacitor should equal the voltage that the battery is providing. So now we know that charge is directly proportional to the voltage, and we see this exponential behavior of the voltage. That means that the charge across the capacitor also has an exponential behavior. So we'll say that the charge at any point here is going to be equal to the maximum charge that the capacitor can store times 1 minus e to the negative t divided by tau. This tau thing is the product between the resistance and the capacitance of the RNC, and it's called a time constant. So if you can work out the units of RC, they are actually seconds. So how do we test that this equation really makes sense? Well, if we start out at t equals 0, we expect that there is no voltage across the capacitor, so there is no charge across the capacitor either. So if I plug in t equals 0 in this equation, I have e to the 0, which is 1. 1 minus 1 is 0. 0 times q is 0. So when we first close the switch, there shouldn't be any charge on the capacitor, and there isn't. Now when we're discharging, again, q is proportional to the voltage. Voltage has this decay behavior. So the equation is q equals q naught e to the negative t over tau. Again, tau is the time constant. So to test this, we know that at time equals 0, the capacitor is charged. It has its maximum charge at that point. So if I plug in t equals 0 here, e to the 0 is 1. 1 times q naught is just q naught. So we see that at t equals 0, the capacitor was charged, and subsequently it will discharge. Now, why do we care about these RC circuits? Well, it turns out that there are lots of very important applications. One thing to note about this is that this discharging or the charging take place relatively quickly. So for the discharging, we first made sure to store a whole bunch of charges on the capacitor, and then by connecting it just with a resistor, we discharge it really quickly. So there's a lot of energy there that can be dissipated in a very small amount of time. So here are some applications. One of them is a defibrillator. First, you have to charge up those defibrillator plates by building a circuit, and you discharge the defibrillator through a patient's heart by touching it on either side of the heart. And what happens in that instance is that the heart contracts due to all of this current all of a sudden going through the heart, and hopefully it will get in the habit of contracting and relaxing, and the heart will start beating again. Another application is the windshield wiper, the intermittent windshield wiper. You know that there is a dial pretty much on the lever that turns the windshield wiper on or off, and as you're turning that dial, you're picking up more or less resistance. So the car battery charges the windshield wiper, and when it reaches a certain amount of current, a certain amount of charge on the capacitor, then the capacitor directs the wiper to wipe the window. And then it waits a while the capacitor is charging again. When it's charged to whatever setting you placed on the capacitor, then it discharges again by wiping the window again. Another example is the camera flash. So it's very obvious on disposable cameras, if those still exist, because to use the flash, you have to hold a button down and then you hear this really high-pitched sound that basically charges the capacitor. So that high whining sound is a capacitor being charged. And then when you hit the button to take the picture, then you see the flash. That's the capacitor discharging in an instant through the light bulb and creating that powerful flash. So RC circuits are used in everyday life. They're very important components of circuits.